Hello there. Today we'll look at Topographic VAEs Learn Equivariant Capsules by T. Anderson Keller and Max Welling. On a high level, this paper proposes a new type of variational autoencoder where the latent variables aren't independent but are organized in a topographic way. Now, what that means, we're going to look at that, but in essence, it means that it can represent transformations in the real world of a certain kind as transformations inside of the latent space of the model. So the whole question is here, how do we build a latent space and a model where this naturally happens as we train it? So we want the real world to somehow correspond to the latent space in a way such that if the real world moves, the latent space moves equivalently or equivariantly. That's where this word is going to come in. So we're going to go through the paper. I have to say I don't understand this fully as well. These variational frameworks, they are always I feel kind of math heavy, and they take a very different approach than the papers I might be used to. So I'm going to tell you what I think is going on here. And if I'm completely wrong, this is entirely possible. Please let me know. All right, let's dive into the paper. This is the first graphic right here that shows kind of an overview over the system. So what do they want to achieve? What they say is we're not going to consider, we're going to try to build a generative model, like a variational autoencoder, but we're not going to consider any kind of data. We're going to consider data, essentially frames of a video. So we're going to assume that what we're looking at is kind of a video, and the transitions inside the video are sort of continuous, sort of monotonic, and slow. So here you can see the 7 rotates slowly and also changes its color slowly, relatively monotonously over this sequence. So what they're going to say is our model is going to take this entire sequence. One picture is going to be kind of the focus here. So this green one is the focus, but we're going to take in this entire sequence right here into the model. And we want the model to come up with a latent representation of the focus image. In this case, it's going to be, we'll jump a step here, is going to be this thing right here. Let's call that, I don't even remember how they call it. Let's call it like Z hat. Okay, this is a latent representation of the focus image. And now, obviously, in a regular variational autoencoder, I could now push this again into the decoder and get back the same image, and I can do so here as well. However, we want something else as well. We also want that if I now transform my latent space in a certain way, and this way is going to be this roll operation in this paper, if I transform my latent space in this way, I want this to correspond to moving forward in this sequence, right? So I have a sequence as an input, and I say, well, my latent space should be such that if I perform certain operations, right? Here in this case, I roll by 10, that corresponds not to the picture that I've input, but to the picture that would be if I were to observe this transition 10 steps into the future. So roll by 10, and roll in this case means you can see here they have 2 of these, what they call capsules. I think they call them capsules, the left one and the right one. And the roll simply means that I take every variable, latent variable, and I simply roll them forward. So this is over the latent dimension. I just roll them forward by 1 step. I do that 10 times. This is, as you can see, this is arranged in sort of a torus here, in a 1D torus. So I can just roll this around, and also this capsule, I can just roll it around 10 times, and that, hopefully, if we train the model correctly, should correspond to not the input image, but the image that is 10 steps into the future. Okay, so that is the goal. Now, we don't want to train a model explicitly to predict 10 steps into the future. That would be would be a valid task, but it's not what this model wants. What this model wants is say, can we build a model architecture and a latent space architecture such that this is kind of happens automatically? And let's see. Well, you can already see kind of how this latent space comes to be. I said this z hat here is going to be the latent representation. You can see that is not the thing that is directly output by the encoder. The encoder in this case outputs many things. So it outputs a z variable. So the z hat is what I call kind of z normalized. The z variable is kind of z unnormalized. So it outputs a z variable for the focus image, but it also outputs this u squared variable, or it outputs the u variables, which we then square. So these u variables right here are output. I'm going to guess this is from this image, and this is from this image, and this is from this image, and also kind of look into the future right here. And yeah, so I have these u variables, and I define sort of a window, a context window around which I look. And I also predict them, I square them, and then I sum them all up. I pull the square root right here, and I divide. So this is why I say kind of a normalized z is what comes out of this, but it's fairly complicated, right? But this is going to, in a way, encourage this behavior. So let's see why that is. And for that, I want to just draw back a little bit to like a regular VAE, a regular variational autoencoder. So if in a regular VAE, you have like an image, this is encoded, decoded, and you get back an image, right? So in a regular VAE, what you assume is you assume that the latent space is sort of made up out of these independent latent variables, latent random variables. They're Gaussian distributed, and yeah, I already said they're independent from each other. And you claim, if I know the latent variables, so essentially if I know the mean and variance of these, then producing an image is easy, right? You can simply train a neural network. I input I input what values my latent variables are, or how the Gaussians are parameterized alternatively. I input that, and I train the decoder to produce a picture from that. That is easy. The question is, if I have a picture, trusty cat right here, if I have a picture, what are the corresponding latent variables? What are the values of the latent variables? That makes sense right here. And of course, in a VAE, we train the encoder and the decoder jointly such that they cooperatively can construct this latent space. Like, okay, how should the latent space look from which the decoder decodes? But I just want to turn your attention to the question of the encoder's job is essentially to take in an image and produce what values the latent variables are. And the latent variables are assumed to be independent from each other and Gaussian distributed. Now, this is where this model right here differs, okay? So this model says, well, we're going to assume we have observed and latent variables, so observed variables x and latent variables t. Observed are, I guess, the images or the image sequences, and t are the latent variables. So this, I guess this would be equivalent to z hat, what I called z hat, they call t. All right, so they say we'll formulate the joint distribution. Note that in this framework, in these variational frameworks, I don't, it's not my thing either, but what you do is you propose a mechanism by which the data and by which the variables are generated. So you, as a designer of the algorithm, propose the structure of how the latent variables work together. And then you have some small parts in there that you say, well, these things I don't know, I'm going to let a neural network do these things. But essentially, you come and you impose a structure upon the world, right? And, if you get the structure correct, your model will work fine. If you don't get the structure correct, your model won't work fine. But this is a bit of a different way of working than, saying, well, I train a convnet to predict. So we're going to propose our structure. We're going to say the joint distribution of observed and latent variables factorizes into these two. It factorizes into this conditional. So if I have the latent variables, right, then what are the images? And times the prior across the latent variables. Now, we already seen this distribution. It's the first one is listed here again. This conditional distribution, that's simply your decoder in the VAE framework. Okay. And that's written here. It essentially says, well, to produce an image, I'm going to put T, the latent variable, into this neural network G right here. And that will give me the distribution of my output image. So this is your decoder in the VAE. Now, the interesting part and where it differs from a regular VAE is right here, where they say, well, how does our latent space look? Well, this is zooming around. Our latent space isn't a independent Gaussians. It's actually this TPOT distribution, this topographic product. No, where does it? I forgot what it's called. A topographic product of student T's model, the TPOT, topographic product of student T. That's going to be our distribution. And that distribution is going to encourage this topographically organized latent space. All right, so we can ask, how does it do that? Note that the encoder isn't here yet, because we've imposed the generative process of the data. The generative process starts at the latent space. I said, if I know what the latent variables are, I can just ask my decoder to produce an image. So this distribution here tells us, the latent variables are distributed like this, and then there we go. Now, obviously, what we want is our encoder to produce the variables, the latent variables, but we also want what the encoder produces to follow this distribution right here. And that's going to be the sort of difficulty right here, because what we know, what we can train with backpropagation is pretty much Gaussians. So, like we can train things where we can apply the reparameterization trick. That's stuff we can backprop through, Gaussians we can sample from efficiently and so on. We have closed form solution for the KL divergences in the objectives. So essentially what we can do in these variational frameworks is Gaussians, okay? Not topographic product of student T's. However, here they show, okay, we can in fact construct a product of student T's. This is not yet a topographic product. It's just a product of student T's distribution from Gaussians. And that is, I take one Z variable and I take a bunch of U variables, and they're all distributed like Gaussians. And I square the U's, I sum them up, I average them, and then I take the square root and I divide Z by that. And this variable right here, that's going to be a univariate student T random variable. This should be kind of known if you've ever taken statistics or use the t-test for anything, okay? And this is already quite familiar, and I can extend this now to the multidimensional case. So if T is a multidimensional student T's random variable composed of independent Z's and U's, then we can construct T as a vector, and that is going to be distributed according to a product of student T's variable. And this should connect to what we've seen before, right? We said that this model's organization of the latent space is pretty much of this form that we saw right here. We have the Z variable divided by the square root of the sum of the squared U variables. And now we learn how we can construct the product of student T's latent space given Z and U independent Gaussians. And that is, now it should connect for you. In deep learning variational frameworks, we can work pretty much only with Gaussian random variables. In this model, we want to work with product of student t random variables. And here is the way how we can construct the product of student t random variables from Gaussian random variables. So that's why here the neural networks will output the z and the u. That's what they will output. Those are Gaussians, or supposed to be Gaussians. And then we transform them by dividing them and summing them up in this way to the latent variable that the decoder receives, which is this z hat, or t, I guess. This is what the decoder receives. So we know that if the encoder output Gaussian random variables, the decoder will receive a product of student t random variable. Now, why is the product of student t random variable special in any way? Because it enables us to, what they call here, introduce topography. In essence, and they formulate this a little bit, what it does is it lets, if some of the u's in this sum and some of the u in this sum are the same, which you can see by the indices, in this case they are not, but if some are shared, that means that the two t variables, not the two z, the two t, so this is one t and this is another t, right? This is t1, this is t2, lots of t. These two variables will no longer be independent. They will actually be dependent on each other. So this is a way how we can construct latent spaces where some of the variables are actually correlated, or in some other way have higher order correlations with each other, meaning that the value of one is not independent from the value of the other one. And that is pretty much a basis for what we want for constructing these topographic latent spaces. So here they say introducing topography. Essentially what we're going to do is we're going to define neighborhoods across our u variables, and we're going to share the u variables according to these neighborhoods, and that's going to make the components of t dependent on each other. And this sounds complicated, but essentially you can imagine, instead of having like 4 latent random variables which are all Gaussians, now we have simply one set of z variables and one set of u variables, and we're going to consider an entire sequence and not just one image, right? So we are going to consider an entire sequence of images like this right here. Every image produces one z and one u variable, and then when we consider an image, let's say this is the focus right now, we consider its z, and we consider a neighborhood of u's, and that's just going to amount sort of like a convolution, like this is maybe a neighborhood of 3. So we're going to consider this u, and this u. So we're going to construct the z on top of the fraction divided by this thing squared, this bubble here squared, this bubble here squared, square root of on top of that, and that's going to be our t. So the t for this image right here, that's going to be this whole fraction. So when we train the VAE, we input the whole sequence, we focus on, for example, this picture, we construct its t by looking at its z and its neighborhood of u's, then we put that t into the decoder is going to produce an image, and then we can apply a loss function between those two. Okay, so that is the loss, that's the loss function, right? The loss function, note that the loss function doesn't say you need, if you roll 10 times, then it needs to be the picture that's 10 times ahead. That is not the case at all. We actually don't have the roll function in here. But even once we introduce the roll function in the latent space, we're not going to explicitly train the model to predict the future. We're simply going to construct, as we did here, the latent space such that this naturally happens. So how are we going to do this? Almost the same. And here, yeah, they talk about capsules. So you can see that they divide this neighborhood structure. So the W defines the neighborhood structure. You can see here some of the U's, they are connected, and then other ones are connected, but these U's are not connected with those. They kind of talk about capsules. Essentially, it's just that they make some of the variables dependent on each other and some not. Or when they do these neighborhood things, they just have two sets of variables. Like they have two sets of Z's and U's. And they only, they construct two T variables, and that's what they call capsules. I don't know why the capsule terminology enters this paper necessarily, but you know, they want to draw a connection here. So temporal coherence. Now we get to how do we organize this latent space such that the roll operation now also gets in. And this is pretty simple. It's actually just an extension of this right here. So here, if you consider these images here as images of a sequence, we always said, well, you need to be connected to sort of your neighboring variables. And now, your neighboring U variables as they are, right? And now we're going to say the same thing, but I'm going to draw the critical path here again. So this, we have a Z variable right here. We have U variables from the neighborhood, okay? And we're going to take the Z variable on top of the fraction, and we're going to take the U variables below the fraction right here, like so, like so, like so. Now, before we do this, before we take the U variables here below the fraction, we're going to roll the U variables according to their distance from the focus. So in this case, this would be simply one roll back. This would be simply one roll forward. So in the language of this paper, what this means is that we don't want we don't want this image, or given a particular position in this image, right? This position right here. If we simply apply the classic neighborhood structure, we say we want this position in this image to be correlated with the same position a step back and a step forward. Now, if we construct the roll like this, what we're saying is no. I want this position to be correlated with maybe this position here and this position there, like slightly behind and slightly ahead. But I'm obviously not going to tell the model what I expect. I simply say, please, this image is one time step, this image is one time step back from me. Please roll the latent space by 1, and that's going to be your relevant variable. And in this case, it's please roll the latent space of this thing 1 forward, and that's going to be your relevant latent variable. So it's not that we train rolling this T variable here, because the T is what finally comes out. We're not training this T to roll forward or back and then predict 10 steps ahead. We're simply saying how you are influenced, you as a focus, how you are influenced by pictures before and after you. You're not simply taking into account their latent variables. You're going to take into account rolled versions of their latent variables in order for you to reconstruct yourself in the training objective. And it turns out, at least that's how I understand it, right? And it turns out, so here you can see the whole process. We're going to take images. We're going to produce mean and variance of Gaussian variables for the z and the u variables. So if you had just a VAE, it would just be this right here, and those would be your latent variables. But not here. We produce two sets, z's and u's. Then we're going to construct the t variables. I don't know why this is on the bottom here, but then we're going to construct the t variables according to this formula. W here is the neighborhood structure. You define it. U and Z are the variables you produced from your encoder, or you sampled from what your encoder produced. And mu here is also a learnable parameter, a learnable mean parameter. And then you're going to stick these t's into, this neural network. Now here it says Z and ZL and UL, but essentially these create T. Oh, here, it's here. You're going to stick the T into your decoder neural network. Remember how do we get the picture from the latent variable? That's the decoder. You're going to stick that into the decoder, and out you get an image. And you train it with the classic elbow, with the evidence lower bound, which says, okay, what I want to reconstruct the picture accurately, right? That's this term right here. I want to reconstruct the picture accurately, but I also want that my essentially what I want is that my t variables are distributed according to this TPOT distribution. I want to enforce that, but I can't, right? I can work with Gaussians. But what I can do is I can say, well, the z variables and the u variables, they must be as Gaussian as possible. So I penalize the KL divergence between what I produce, which is this right here, and the Gaussian, like a pure Gaussian. This has a closed form. I can calculate KL divergences from what I produce with Gaussians, no problem. Okay, and that's the training loss. And I simply average that over the input sequence, and there you go. Now, the evaluation of these things, I have to say, after reading through the experiments and the evaluations, this is a paper, kind of an idea. At least I feel so, right? Correct me if I'm wrong, but I feel that this is sort of an idea paper. It's like, here's an idea. It works if we, specifically construct a data set for it. And if we specifically, also the experiments appear to be kind of fiddly, like you have to really, get your parameters right to make this work. But if you do, then, the model behaves as you expect. And so they measure things like, is the rolled version of the latent variables really equal to the latent variables a couple of time steps ahead? And things like this. And they produce these maps. So here is one where the latent space isn't a 1D torus like we looked at. So 1D torus is this, right? So you go around. Sorry. This is a 2D torus. So a 2D torus is like a plane. And if you leave here, you come back here. And if you leave here, you come back here. So if you roll this up, and then you have a pipe, and if you close the pipe, you have like a donut. So that's a torus. So if they have a topographic space like a torus, they simply apply that to MNIST. The test set sort of looks like this. I don't know if you want to read something into this, like, feel free. I'm not sure. But when they go with the sequences, so here you see like the sequences, I think on top is what they input, and then this is the continuation that the model doesn't see. On the bottom is what the model produces. You can see the model does get to a point where it understands how these sequences go. Here, right, it goes larger, and then it kind of flips around to the smallest. This is a expected behavior. Here as well, the rotation. Model continues the rotation, and it turns out even if the model is just trained with, they have these experiments, even if the model is just trained with single transformations, so either a rotation or a scale transformation or a color change, it can generalize to multiple transformations at once. As you can see right here, colors and rotations the model can generalize to that fairly well. Okay, I don't want to get too much into the experiments because I'm not sure how important the numbers here are. Safe to say, if you construct this model and if you apply it to the problems where exactly this is needed, and if you get the hyperparameters right, then this model actually works. It's better. Whereas a regular neural network, it could not easily incorporate the concept of these slow changing transitions. It would sort of have to learn, okay, what color comes after red, orange? Okay, what color comes after orange, yellow? Okay, what color comes after yellow, green? I guess the other model has to learn that as well. But then this model, it cannot represent the transition in a sequence as it has to learn it as a parameterized function rather than being able to map it to an internal transformation of the latent space, like the topographic VAE can do. Okay, that was it from me. I'm not competent enough to tell you how big of a step this is. It feels to me like a little step. It might be a giant step. I don't know, okay? It feels to me like it's kind of an idea paper to show something neat that you could do in an idealized case. It might be that this is a much bigger deal than I think. I thought it was a cool paper. I thought it was a neat idea. It's written, even though it's, I think, kind of, more high level, so I'm not as competent at it, but I could still make sense of it. So if you enjoy this, give it a read. Let me know if you have any comments, and that was it. Bye-bye. Thanks.